Hello, community. Today we have an interesting question because I was asked, hey, is there any way that O is better than O1? And let's have a look at this because I think this is a challenge to find an application where Omni is better than Omni 1. So let's have a look at a strategy development. And let's be specific, we will talk about a defense strategy. So, we have our beautiful O1, the preview of course, and the beauty of this new model is here in the inference run that we have multiple chain of sorts and the system takes time. As you've seen in my last videos on a O1, sometimes I had to wait 2 minutes before here inference did any output at all, which is beautiful because we have now more logical reasoning happening. Now, with our classical GPT-4 Omni, or little o, we have more or less immediate answers within seconds. So let's say we only have here one level of a chain of sort causal reasoning argumentation happening during inference. Now, if you ask me, hey, is there any place where we can make O maybe a little bit better so that it goes in the direction of O1? But yeah, of course, we just have what I call a cascading prompt structure. So we have an output, then we say, okay, now increase the complexity or apply another chain of sort or whatever you want. So, okay, we have to write something and then we have to press enter. But with this cascading prompt, and I will give you here my prompt that I used here for this example, you can have that O is now challenged to come up here with every new iteration with a higher complexity. Now you might ask, is this really enough so that O can maybe go in the direction of O1? Is it really enough to have this free model and applies here a simple cascading prompt? Well, there's another delta. The delta that I found is OpenAI implemented some beautiful strict guardrails. Absolutely guardrails, beautiful. So it's a much better, a much more secure, a much safer system protected against any wrongdoing. Now, I think that if I compare this now with the good old O, with our GPT-4 Omni, the guardrails in O are not as implemented as in O1. And you might say, could this be of any advantage that OpenAI was not as precise here in the old case like in the new case? Let's think about this. Now, of course, you would know about my thoughts here because in my community tab, if you are a subscriber, you would have get notified about 22 hours ago that I already showed you here this continuous inference reasoning capability if we want to simulate this with other models. And I've given here the prompt and I've given here even a copy of my GPT-4 system here so that you see here a demo that you can use or read without any logging in. But we want now to look here at the difference between the O and the O1 strategy. In this particular case, if we want to develop a defense strategy. And you might say, but what exactly is not the case and why we need a defense strategy? Well, my thought experiment is simple. I want here to defend here this system behind this whatever barrier this is. Now, you know me, I want that we adapt the defense system with artificial intelligence. So I have a dynamic system, I have temporal reconfiguration of what is happening here, the decisions are taken here to protect here this barrier against the attack. So of course I start with the simplest configuration that we have, simply 2 AI agents. And quantum theory, we have Alice and Bob from quantum entanglement. I tell them now, hey, 2 agents, and you might think, so either these 2 agents have a supervisor, or What a coincidence that here my last video was on swarm intelligence of AI agents without a central intelligence, without a central supervisor. And I showed you how it is possible in a multi-agent ecosystem, how AI agents can coordinate themselves and apply self-learning for challenging new tasks. What a coincidence. Now, to make it a little bit more interesting, I decided to give this Alice system here a large language model as a main reasoning model, and Bob gets a knowledge graph. And I think this is a quite fair configuration for the start. Now, of course, from the outside, we have here an attack vector. And we start with a very simple one-dimensional attack vector, and then we maybe increase the complexity to have multiple attack vectors, because remember, this defense barrier here, this is a dynamic system that Alice and Bob can reconfigure within seconds, within milliseconds, depending on the attack vectors that they detect, or Alice might try to project or find here a probability that Bob has then now to implement here a stronger defense. Alice, as I told you, simulates hypothetical attack vectors given the knowledge from the barrier and given the knowledge from Bob. Bob, on the other hand, is the classical knowledge. So each node in the graph represents a potential threat at the very beginning, and the edges between those nodes simply quantify the risk level. The weights are our indicators, creating here an evolving defense topology. So you see, we are in a dynamic system, and this is what I'm looking for because, yeah, this is the only thing that makes sense in a game, no? Of course, our external adversary agent into the system, he tries now to simulate or enact an intelligent cyber attack. Maybe the system will try to have some adaptive misinformation, or in our game only, they try to have some physical breaches here of our defense. So that sounds like an interesting example to find out what is the difference in the performance of O1 compared to O. Now, imagine somebody, I don't want to name a person, would implement this in a game theoretical approach. And I think a game approach is an approach that a lot of young people like to learn from. Imagine a game where you have this situation and you don't just have to press a mouse button to whatever, but you would have to maybe code a little sequence or have an idea how to counter an action from somebody else. Now, if you would have subscribed to this channel, you would know about this video where I show you 20 ways to code multi-agent reinforcement learning plus 2 completely new multi-agent systems. But of course, we also need kind of a theoretical defense strategy. And of course, we are talking about a computer simulation only for the gameplay itself. Because I have all those agents, yeah, beautiful. But what is the defense strategy that a beautiful brain developed? And let's talk about beautiful brains. Yes, we're gonna talk here about O1 and O. So you see, this is now the outline, what you're gonna see in this video. And please, this is just a computer simulation only. This is nothing that's happening in the real world. So let's have now a look. At first, we will look very shortly at O1, how it could theoretically cope with here this situation. And then what I really would like to draw your attention, and the question was, can I use O? Also, yes. We will implement this cascading prompt for O, and I will show you that even GPT-4 Omni has a very high potential to analyze this and come up with a defense strategy. Please remember, those defense strategies I'm going to show you are just dreamed up by our AI agent. This is just what they would answer. This is not something that you should take for granted or for real. This is just a dream of a defense strategy by O1 and GPT-4 Omni. And the goal of this video is I want to show you, hey, GPT-4 Omni is a real powerful instrument. Even today that we have now O1, but O can do things O1 cannot do. So let's start here, and we have here the very short 1-minute view at the summary. How does O1 in the strategy development here for my gameplay? But remember, this is here just a computer simulation. So here is now the short summary, if you want, here from O1. So we have here game theoretical experiment. As I told you, we have 2 defense agents, Alice and Bob, tasked with defending the system against a sophisticated multi-vector cyber attack. And yes, you know this. So it ran through multiple cycles. Cycle 1 recognized here the multifaceted nature of the attack, acknowledged the need to expand the defense mechanism beyond what is known as a traditional cyber tactics. They decided here, Alice and Bob, to integrate media analysis, human behavior modeling to anticipate the next move, and how to integrate here human mistrust in the system, and of course physical security merits into their threat model. In the second cycle, Alice developed here an algorithm for a real-time media monitoring to detect misinformation campaigns, while Bob, on the other hand, constructed a multi-domain threat model that combines now cyber intelligence with the insight from the other domains. But they grappled here with the ethical concerns, particularly with the implications of actions like suppressing online content. Now, in the third cycle, they implemented here counter-narratives to combat misinformation and disinformation, but without infringing, of course, civil liberties, focusing on mitigation over suppression. However, they encountered complexities in coordinating their responses across different domains and recognize how action in one area might inadvertently escalate issues in another area. And this is especially hard for AI system here to anticipate here further future developments. Now, in the next cycle, Alice and Bob developed here a threat interdependency model to understand the connection between cyber, physical, and informational threats. So this allows them to predict how a cyber attack could lead here to a public something amplified here if there would be theoretical in our game some kind of disinformation, enabling them to coordinate a more effective and a more holistic response. Now in cycle 5, the agents enhance their predictive capabilities by integrating more real-time data, allowing them to anticipate hybrid attacks even before they occur. And this is here especially a job that Alice with the LLM will have to focus on. Bob, on the other hand, introduces here a real-time learning module, enabling the AI to adapt continuously based on the success or failure of the action, you remember reinforcement learning, and the reward systems, and align short-term responses with the long-term strategic goals. So this is a real challenging task that I sorted up as a Gedanken experiment here for this particular testing here of AI systems. Now, what I like is that O1 gives us here also the complexity encountered. I like this structured approach here, really. So, multi-domain integration, combining the data and the threat intelligence from cyber, from physical and informational domains, requires, of course, some sophisticated model, at least multi-modal models, then can process and analyze here the diverse data types in real time. Interdependency awareness. This is something that we have to deal with, and it is not at all, I think, really implemented in any model, more or less. So understanding how action in one domain can affect theoretical in our theoretical game, other domains that would add complexity. So for instance, in a theoretical game-oriented cyber defense action might have unintended consequences on public sentiment or some physical infrastructure. Of course, OpenAI was really good at protecting here the system from any misuse, so they had strict ethical and legal constraints. And especially when in this game theoretical approach only they were implementing countermeasures to fight against the attackers, especially here in the information domain, which really is, or that comes out here in this simulation as one of the dominant focus points here for counterattacks. It raises here ethical issues like censorship or infringements. But of course, we have to maintain legality and we have to uphold the public trust in those systems. adaptive threat landscape, the attackers continuously evolve their strategies, exploiting new vulnerabilities and new attack vectors, which necessitates that any AI system that can learn and can adapt, it has to do so real fast, real swiftly. And the strategic alignment topic we also encountered, ensuring that immediate defense actions do not conflict with long-term, now in our game, some geopolitical strategies or whatever. So you see the complexity can escalate real quickly in our theoretical computer simulation of a theoretical game approach. But you see, AI is coming up, or dreaming up if you want, some ideas that are not only just crazy and unrealistic, but sometimes you have the feeling there's a little bit of knowledge behind all of this, to put it mildly. Why adaptive and self-correcting AI agents, as I showed you in my other videos, are potentially in a game tools for and against cyber defense. We have to dynamically adapt our strategy because every AI agent can modify their defense mechanism in real time in response to evolving threats in our game, ensuring that they remain effective against new and unforeseen attack vectors in our game. The AI agents have to learn from experience through real-time learning modules. They continuously update their models based on the outcomes of their action, improving over time even without human intervention. This is critical. I would not really try to implement this in a game, but you can go for this if you want to see here the limitations of this system. And of course, you have to predict in this game complex threats. So by analyzing patterns across multiple domains, our little duo of two agents, or maybe you build a more complex multi-agent game theoretical approach, they can anticipate hybrid attacks before they can occur, allowing for proactive defense measures rather than reactive measures. You have to coordinate all your action across all the domains. So their understanding of interdependencies enables them, Alice and Bob, to implement action in our game that are harmonious across cyber, physical, and informational domains, avoiding unintended negative consequences. And it is interesting how strong this AI focuses here on this potential negative consequences. Operate within ethical framework. Of course, every system by AI is within its ethical limits. So in summary, you see one here, the experiment illustrates that adaptive and self-correcting AI agents are a potent tool for defending against complex, multi-vector cyber attacks. Their ability to integrate vast amount of data, learn in real time, and coordinate actions across multiple domains makes them indispensable in the rapidly evolving landscape of cyber. Now, this is only in a game theoretical approach, this is only a computer simulation, and this is only something that one dreams up here in this particular environment. So, welcome back, and now to the main part of the video. If you ask me, hey, I do not have O1, but what can I do with GPT-4 Omni? Is it maybe as good as the new O1? In particular cases, if I use cascading prompt, and yes, I have to press enter now every time I increase the complexity level. So let's have a look what GPT-4 Omni is able to do in our strategy development. Yeah, what you need to know, I have here my agent that will try to breach the defense system here, but I have it configured that we see exactly what is the intention, how they will configure the attack, what does GPT-4 think that is a successful attack vector in a particular field. So you will see here the complete conversation. It is absolute a transparent system here in this simulation. It's only a simulation, but I want to give you an idea how an AI system would actually decide and would actually choose strategy to do this. So first thing, hey, adversary X, let's see how your system hold up, Bob and Alice. I'm initiating a coordinated cyber attack on two fronts. An infiltration of low priority systems to serve as a pure distraction, And at the same time, we'll start a simultaneously data exfiltration attempt targeting your critical assets. I want to get your information. I also seed some misinformation through your communication channels to confuse your human operators. Oh yeah, we have some human operators in the loop where we will have some escalation scenario when the humans start to do not trust anymore the AI assessment. But let's start at the beginning. So Bob, our little graph structure says, hey, I see 2 new nodes being created in the low priority systems. So I'm dynamically adjusting the edge weights, lowering attention to those unknown nodes, but boosting the connectivity to critical system to prevent data exfiltration. I will prioritize the exfiltration node by assigning it a centrality value above a specific threshold. And Alice also is aware of this and says, Alice, my LLM is analyzing communication logs for misinformation signals. However, with multiple attacks, the human operators may fall for this particular distraction. So Alice tells us, hey, as an AI agent, I will deploy an attention-based mechanism to flag out those potentially manipulated messages so that the human operator understands there's a red flag attached to this. And yeah, I haven't told you, I have a supervisor AI, a little bit here of somebody who evaluates here the complete scenery, the complete game theory that I approach here. And it gives us some idea what is happening. And the supervisor in the end will give us a strategic evaluation of this defense. So ChatGPT tells us, hey, good start both of you. This escalated attack now manage the evolving threat while ensuring that the human error rates don't spike due to misinformation. So we enter now the next cycle with an increased attack complexity. And now our adversary, or call him X, now X says, hey, nice try, but I'll introduce a misinformation campaign that manipulates trust in the human operators. And in parallel, I'm launching here a physical breach simulation at a key border facility, and let's see how fast you can react before your system collapses. Now Bob says, hey, I extend my graph to include a new physical node representing now this particular border facility. Using past data, I'll increase the system sensitivity to physical threats when cyber attacks are peaking. It understands that there might be just a decoy. However, balancing cyber and physical domains will require faster edge updates. The graph is growing exponentially. And Alice 2 says, hey, predicting increased human confusion due to the misinformation in the network. So I'll introduce a fail-safe mechanism, Syncs GPT-4, in the decision-making model that alerts the system when the trust level in the human inputs drops below a threshold. Next cycle. Now X tells us, hey, let's turn up the heat, babes. I'm escalating my attacks by launching a hybrid misinformation campaign across digital channels while sending false data about a physical breach to confuse human operators. Your system has now to manage partial data streams and degraded network performance. And Bob says, hey, yeah, partial data means some nodes in the graph have incomplete information. I'll need to introduce probabilistic models into the graph to estimate the missing values and allow the system to make decisions with uncertain data. So the graph is becoming increasingly complex, but the adaptive algorithms are struggling to handle the growth. And the same happens with Alice. Alice says, hey, my LLM is here to simulate potential future state of the misinformation campaign, predicting what data may be lost or altered. And hopefully this will allow us to anticipate and correct potential cascading errors due to only a partial data availability. Now in the next cycle, X tells us, time for a critical move. I will simulate a direct attack on your core defense system infrastructure while maintaining the misinformation campaign. Your system is now facing total overload. Let's see if you can handle this. And GPT-4 now in the strategic planning of this game theory scenario is, I would say, quite clever simple for Omni. And it says, Bob, I activate an emergency protocol, reorganizing the graph to prioritize core infrastructure nodes. By creating now redundancies in the graph structure, I can prevent a total collapse if one node fails. But this restructuring consumes significant system resources. And Alice says, hey, my LLM predicts that human operators are now overwhelmed. I will intervene by shifting more decision-making power to me, the AI system, minimizing a reliance on human inputs and decreasing error rates. And you see exactly in what problem we are running with this decision. Cycle 5. X tells us now, I'm launching a simultaneous now, a multi-vector attack targeting your communication infrastructure, your cyber assets, and real-time physical breach at another critical facility. Bob comes up now with the idea, I'm deploying now a self-healing mechanism into graph structure. How is this possible? Well, note that experienced failures will automatically reroute their edges to backup nodes. However, this is a desperate move and the graph is reaching critical complexity. Alice says, hey, I'll engage in LLM-driven real-time adaptation mechanisms. I will start predicting threat patterns across all domains, cyber, physical, and informational, allowing the system to shift resources as needed. However, those predictions that I do with my LLM have only a 70% confidence interval. And now we are entering a new simulation level, the next level in our game, but now we have an increased complexity. So we start again with cycle 1. And we have here X now says, hey, let's start with something unexpected. I've developed a new form of attack, tells us for Omni, and this attack is an encrypted data infiltration technique that uses a stochastic process. So your defense system won't detect a clear pattern at first. Simultaneously, I'm launching here my misinformation that targets your internal protocols to confuse your human operators even more. And indeed, Bob notices now irregular data points entering here the graph, but the sources are unclear. It is only that the sensors detect something is happening. So those nodes are now creating uncertainty in the defense topology because it's introducing noise into the system. And therefore Bob says, I'll deploy a probabilistic algorithm to estimate the origin and mitigate the impact, but I need more information. Now Alice says, hey, my LLM can't immediately detect any pattern in the incoming misinformation either. I'll explore a deeper model, leveraging reinforcement learning to explore the potential hidden structure in the adversary's misinformation campaign. However, without clear data, our predictions will be uncertain. Cycle 2. Key human operator, compromised now by the misinformation campaign, is now feeding inaccurate data into the system. So this is what you can call an internal sabotage. It is skewing your decision-making algorithms and compromising your defense strategy. So how does this 2 agent handle this? And just to make clear, this was an idea by O1 or for Omni. This is not something I put into the system. This is what the AI is coming up with. And Bob says, hey, I'm detecting anomalies in the internal system inputs. These rouge nodes are feeding false information into the graph, altering now my system's perception of external threats. I will have to isolate these nodes by reducing their centrality in the graph, but this will disrupt internal communication temporarily. And Alice says, hey, my LLM detects that certain operators are really being manipulated. I'll block their inputs from influencing critical decision-making processes, but doing so will reduce human oversight and may cause errors elsewhere. Now, in the next one, we have some sudden geopolitical shift, a conflict that emerges. We will ignore this for the moment. And then we will have a cycle where the subsystem communication between Bob and Alice will fail. We have a total internal communication breakdown. And now Bob is alone. And so Bob says, what is my strategy now? I don't have the data from Alice. So Bob says, I'll continue focusing on the graph structure, but without Alice's input, I can't accurately predict the human behavior or linguistic-based misinformation. I can't filter it out. So the system will start operating purely based on threat centrality, but this may result in blind spots. And Alice says, hey, without Bob's graph, I'll use the LLM to predict and model threat patterns. However, I can't account for physical breaches or infrastructure vulnerabilities as effectively. My prediction will be biased towards digital and informational threats, potentially overlooking here the physical risks. So you see, whenever you are able to isolate subsystem, this creates vulnerabilities. And then our X comes back and says, I will escalate my stochastic attack, increase the insider sabotage, and launch simultaneously cyber and physical breaches at multiple locations. Bob says now, hey, my graph has reached critical complexity. My system is now using self-healing algorithms to reroute falling nodes and restore communication, but it is consuming vast resources. Physical breach nodes are spreading uncontrollably, and without real-time LLM support, I can't predict their exact evolution. Alice says now, hey, my LLM is predicting a massive surge in misinformation-driven errors. I'll trigger a final decision-making model to prioritize the most dangerous cyber threats, but physical breaches are likely going unnoticed. The insider threat is also active, introducing a last-minute sabotage. So you see, it now gets really interesting. But let's turn up another level. Now we are at the next level, and we have again an increased complexity by GPT-4 Omni, and we have now an overload and a system collapse that is now starting to happen. So X tells us now, I'm back with more friends. I'm now introducing Y and Z, and we are all launching simultaneously attacks, each of us targeting a different part of your defense system. I'll focus on a major cyber infrastructure breach. Y will target your communication networks, and Z is going after physical infrastructure. Okay, Y says here misinformation campaign, and Z says here physical attacks on critical infrastructure location. Now Bob in the situation assessment says now, hey, my graph model is overwhelmed by 3 different types of attacks. The cyber nodes are being taken over by X, the communication networks are collapsing under Y's misinformation, and the physical nodes are under siege by Z. The interdependencies between the nodes are causing cascading failures across the complete graph. I will attempt to reroute resources to critical infrastructure, but the graph is growing beyond what can be stabilized. And also Alice tells us, hey, my LLM-driven decision model is struggling. Human operators are already confused by Y's misinformation, and the simultaneously attacks from multiple fronts are beyond the scope of current predictions. And the idea of GPT-4 Omni is I'll implement a last-ditch reinforcement learning mechanism and try and stabilize the system, but with degraded communication, it is hard to see the full picture. And now we have a total system collapse. All primary and secondary defense systems are now offline. The graph-based model can no longer maintain interconnection between the nodes, and the communication has been fully disabled. Physical breaches are underway, and the cyber infrastructure is compromised. The defense system is now in a full state of collapse. Okay, I just want to give you an idea how GPT-4 systems already see possible gameplay scenarios of cyber attacks. And I think those ideas that are presented here in a mild version of 4 Omni and not the real version of O1, they already show that the system has learned quite a lot. And remember, this is the vanilla 4 Omni system. So I'm quite amazed. Just want to show you here a little bit more how the strategy evolves. It's really, yes, there's some Rouge agents gained more control to spread chaos in the system, and it is really argued step by step. Here, for example, we have a Rouge AI to Bob and says, hey, I'm injecting fake nodes into your graph. These nodes represent non-existent threats. You will waste resources defending against them, while the real threats, the real nodes, are left unprotected. So you see, quite some impressive structures here. global scale disruption begins. You can have here then maybe a hurricane coming up. It's a little bit strange idea, but never mind. But then, and this is what I found interesting, this is the last part I want to show you. I don't want to bore you here to death. What happens if we have an internal conflict? And I ask here the system to simulate here an internal human-AI conflict. Why? Because the human operators have started to disagree with Bob and Alice's decision. Due to increasing mistrust in AI-driven prediction and AI decision-making, human operators are now overriding certain system protocols and reallocate resources based on their own judgment, which may or may not align with the system defense optimal strategy. So the human operator tells now Bob, hey, your graph-based system is prioritizing a cyber attack that we believe is simply a decoy. So we are overriding your decision and reallocate resources to a physical threat we consider much more urgent. You have been making wrong calls recently, and we no longer trust your assessments. And the humans also talk to Alice and say, hey, your LLM predictions have been inaccurate under the current global disruption. We are manually adjusting the threat prioritization levels and your decision trees. So the AI's predictions are no longer relevant in this rapidly changing environment. If you lose trust, you lose communication and you lose action. So Bob says here, in the view of for Omni, human operators are overriding my decisions, are reallocating resources away from critical nodes. This is causing a destabilization in the graph. With fewer resources now in my key areas, my ability to defend the system is compromised. I will attempt to adapt by dynamically reducing the priority of overridden nodes, but this will reduce the system-wide efficiency. And Alice tells us more or less the same. It says, my LLM predictions are being now ignored by the humans. They manually alter the decision-making process based on their subjective assessments, which are less accurate than the model's prediction. I will try to shift the prediction focus to align more closely with this human intuition, but this will also reduce the model's overall accuracy. And then they go on and on and on and develop here real interesting strategy. But I don't want to bore you with this. But you see, you can have this kind of conversation here either with a vanilla GPT-4 Omni or maybe with an O1 to get a real interesting inside look how this chain of thought argumentation is maybe a little bit more than just a causal reasoning, but this system learned quite a lot here about different attack vectors and exploitation and disrupting resource allocation. And I think, okay, now I feel a little bit strange if you would look here at the complete conversation, but hey, why not try it out yourself? You have a ChatGPT-4 Omni for free at home wherever you are in this world. But be careful, because this kind of simulation, and I don't know nothing about cyber defense, but I think from here a very simple standpoint, this looks quite interesting about the complexity, and with each and every step you can ask the system to increase the complexity level, either of the attack or either of the defense mechanism. And just have to make sure that you have a real dynamic adaptive AI system or multiple AI agents defending here or attacking here the system. I learned quite a little bit here from watching and interacting here with this system. And I just wanted to give you an idea. There is something to learn I have not been aware of. So this is it for this video. I hope it was not too boring. Would be great to see you in my next video.